and we are very happy to enjoy this workshop, but also to fulfill the strategy of our Hellenic Institute of Nuclear Physics, which is the synergy, the collaboration. It was founded on the basis of the collaboration between three universities, the University of Ioannina, the University of Thessaloniki, Aristotle University of Thessaloniki, and the National and Kapodistrian University of Athens. Along the years, these collaborations were spread out over all the world. And here is the sound result of this effort, with 16 invited speakers from the United States, South Africa, Europe, and China. We very warmly thank all of you and all the participants. Now is the time to open this workshop, and I call Professor Panagiotta Kandi, who is the Vice Rector of the University of Ioannina.
Good morning to all. Dear Dean of the School of Natural Sciences, dear Head of the Physics Department, dear members of the Organizing Committee, dear distinguished guests and participants of the workshop. It is a great honor and joy to be with you here today at the Conference Center Karolos Papoulias of our university in order to participate in the opening ceremony of the 7th workshop of the Hellenic Institute of Nuclear Physics. As we heard from Professor Pakou, the Hellenic Institute of Nuclear Physics was established in 2008 by 3 nuclear physics laboratories from the University of Ioannina, the Aristotle University of Thessaloniki, and the National and Kapodistrian University of Athens. It organizes the HINP symposia on a regular basis at a different institute or university in Greece each time, bringing together distinguished guests, scientists from all over the world and the Greek universities. This year's symposium is co-organized by members of the Group of Nuclear Physics of the Physics Department of the University of Ioannina, a group which comprises leading scientists and dear colleagues of our department who actively and persistently conduct front-end research in various topics in nuclear physics. As always, in the HINP Symposia this year also, recent developments in nuclear physics will be presented and discussed, new perspectives and ideas will be exchanged. The HINP Symposia provide indeed a vivid and much-needed forum where the synergy of leading scientists based in different institutes around the globe and the members of the Hellenic Nuclear Physics Society can be realized. Most important, young colleagues and students are exposed in an international scientific environment of the highest standards, where they can learn, emulate, interact, and get inspired. Last but not least, every workshop and conference conducted in our university is an open window that invites the scientific world to Ioannina and at the same time enhances the place of our university in the international academic map. I would therefore like to welcome all of you to our university, the University of Ioannina, and I hope you will have a very productive and pleasant workshop. Thank you very much.
I would like now to call the Dean of the School of Science, Professor George Floudas.
I think the microphone is not working.
It doesn't work.
Is it working?
For that reason I asked before.
Actually, it doesn't work. Anyway, I can start, no problem. Okay. So I also like to welcome you all to Ioannina at this workshop organized by Professor Pakou. Professor Pakou has been a distinguished member of the physics department, and she has organized a series of such seminars and workshops in nuclear physics. It's a very small department, it's a very small group within the Department of Physics, but it's a very dynamic over the years. And therefore, I would like to welcome you all here. I also see that there are many people from abroad, not only from Greece. I think in previous case there were less people from abroad, if I remember well.
Yes,
right?
yes. So we spread out now.
Right, very well. Okay. I see there are also quite a few people from the States, I recognize in the program there are people from Texas A&M, for example, and so on. Now, I will tell you a story, very briefly, 2 minutes only. A story when I was traveling from the States to Europe, I had a lady next to me. She was a part of a group of about 15 people that were doing walking tours or hiking tours. So she was traveling to Greece because she had a map of Greece. So I asked her, where are you going? So presumably I told her, you go to, no, sorry. Presumably you go to the islands. She said, no, we don't go to the islands. So she showed me a map, and she said, well, we go to the unknown Greece. And unknown Greece is this area where you are at the moment. So Epirus is the unknown Greece. So if you have some time after the conference, it would be very nice if you can explore this area, because it's very unique. It's very well known within Greece, but is unknown outside of Greece. So take this opportunity, not only scientific, but also non-scientific.
But we are going to visit the ancient theater of
Dodona. But that's not enough, I have to say, right? Okay. Okay, so I wish you all the luck, yeah? All the best.
And now I call the chair of the physics department, Professor Samuel Cohen.
Thank you very much. Okay. Dear Vice Rector, dear Dean, dear participants, dear friends. As the head of the Department of Physics, it gives me great pleasure to welcome you to our university and to the 7th workshop of the Hellenic Institute of Nuclear Physics. A special welcome goes to your distinguished invited speakers and to participants who have come from around the world to support the event. And I hope that the workshop will provide an opportunity to share recent advances in various topics of nuclear physics and serve as a catalyst for strengthening national and international scientific collaborations. I'm happy to see that although this is a thematic workshop, participation is high, I can say, and this year, and that you have a full and stimulated agenda for the next 2 days. I'm further pleased to see many graduate and even undergraduate students in the audience. This is especially worthy of note as your workshop will provide a platform for young people to get acquainted with the community and keep track of new aspects and perspectives in the field. I would like to take the opportunity to say a few words about the Department of Physics, which is one of the historical departments of the University of Ioannina. It was established in 1970 when only the departments of philosophy and mathematics were in operation as part of the Aristotle University of Thessaloniki. Today, our manpower amounts to 33 members of faculty staff that are about to increase to the number of 37 quite shortly. Additionally, there are 9 members of laboratory teaching staff and 7 members of technical and administrative staff. The department hosts more than 1,000 undergraduate students and 60 postgraduate students, as well as over 40 PhD candidates. Our main goal is to provide our students with high-quality education in theoretical and experimental physics, as well as in other related disciplines, through a well-designed study program which has been accredited by the Hellenic Authority for Higher Education. We put equal focus on conducting high-impact research, attracting competitive research funding, and pursuing collaborations with science from Greece and abroad, like today. As part of our efforts to gain visibility and enhance openness, it is always an honor and a pleasure to have scientific conferences organized with the contribution of our department. I'm sure that our colleagues from the organizing committee have done a great job to put everything in order for this event, and I trust that you will leave Ioannina with the best of impressions. I don't want to take any more of your time. I just wish you again all a fruitful workshop, and I hope that you will also have the chance to enjoy your stay in our beautiful city. Thank you very much.
And Professor George Souliotis, the chair of the Hellenic Institute of Nuclear Physics, please.
Thank you very much. I would like to welcome all of you. This is a great opportunity for us to be together. This is the 7th workshop of our institute, and we have, through the years, we have enjoyed a collaboration between colleagues in the Greek universities, and also the most important is the collaboration with our international people. I'm very happy and very pleased, and I would like to thank very much our invited speakers that came from all over the world to be with us and discuss their results, and also initiate or continue existing collaborations. I think one of the topics that especially expresses myself is the role of fundamental research in nuclear physics, which is very important to be maintained and cultivated nowadays, that everything sounds like applications, which is more than true in our small country, in Greece. Fundamental nuclear physics plays a pivotal role in understanding the universe, and we see this both in what we are learning in the micro world, as well as its applications to the macrocosmos, to the universe. So that's very exciting, and I would like to share this excitement with all of you, and especially our students and graduate students and undergraduate students. So thank you very much, and we are looking forward to a very productive workshop. Thank you.
This year, the workshop is under the auspices of the Hellenic Nuclear Physics Society, and so I call Professor Christos Tsabaris to take the floor, please.
Thank you very much. Dear Rector, dear Director, dear organizers, dear participants, I would like to greet the organization of this symposium from the Hellenic Nuclear Institute that brings scientists from Greece, but also from other countries of the world. And I would like just also to mention that it will be very interesting that the topics will be related in theoretical and experimental nuclear physics. I would like also to wish you to have a very effective symposium the next 2 days. And I would like also to say that the Hellenic Nuclear Physics Society, knowing the significance of this symposium, they made it under its auspices. Thank you very much.
Very nicely, we are earlier than what we have organized for 9:30, so George Souliotis will come here as the chair of the first session. If it is more easier for you, you could stay there or here.
Okay, so we are starting this very first session of our workshop with Professor Yennello on a very exciting and intriguing topic on excited states of nuclear matter that may have shapes, toroidal shapes. So, Professor Yennello.
Thank you very much. I'm thrilled to be here. It's my first time in Greece in this beautiful area. I guess just listening to George's introduction a minute ago, I think it's really important that we explain to everyone the synergies between fundamental nuclear science and fundamental science in general and applied science. And I know my lab, we spend about 50% of our time doing applied stuff, but the other 50% is basics science, and these two things are very synergistic in terms of both the workforce and the intellectual and physical infrastructure between the two. And so I think this is a really important point. And so with that said, I'm just going to talk about some of the discovery science here today, but I'm happy to talk offline about the other stuff. But it's very important that we communicate to the world really the synergies there. Okay. after the editorial. So I'm going to talk about a recent experiment that was done at Texas A&M, which was a search for toroids in excited nuclear material. So this was a follow-up on some previous experiment. And I have to call out Andy Hanneman, who was the graduate student who's really responsible for all this work, and certainly all the rest of the people in SJY group. And nothing at the cyclotron would happen without our exceedingly talented operations staff. So just to give you an idea of what we're going to talk about, I will give you some background and motivation on toroids. And actually, I don't have time to go into a full history of searches for toroids and nuclei, so I'm going to give you a very brief one. And then talk about the detector that we used, Faust, some of the experimental details, some calibrations, the analysis, and then we'll come up with some conclusions. Okay, so the history of looking for toroids in particular in excited nuclear matter goes back into like the 1950s with an unpublished thing by John Wheeler, who said or postulated, could a nucleus form this exotic shape? But like any good professor at the time, he said, I've got a bunch of really smart graduate students, and so if I want smart people to think about this problem, what should I do? Is assign it as a take-home exam, okay? So in 1963, actually John Wheeler at the University of Princeton assigned this problem, and you probably can't read all the details, but basically it was to calculate what might be possible in terms of a toroidal nucleus. This led to Wang, who was a student of Wheeler's, to actually take the challenge much further than just a take-home exam and actually spend many, many years working on toroidal nuclei. So faculty, remember, your graduate students are really smart and they will go on and do great things, and you can tap into them with an appropriate exam. But anyway, so Wang was able to actually, looking at the nucleus in terms of a liquid drop model and using some statistical assumptions, find this area where there would be a stable toroid at high angular momentum. Oh, sorry, I do have a pointer here. So this is what we think of, this is our stable spheroid, and then he was able to map out this area where one would expect a stable toroidal configuration. So this was done fairly early, really looking at it in terms of the liquid drop model and classical mechanics. He went on, and there's a huge body of work of which I don't have time to go through, but certainly went on later and included elements of the shell model and the toroidal shell model, and came to this set of figures where it was predicted that at certain angular momentum, there would be particular excitation energies at which the toroid would be stable. And so in doing that, this prompted a colleague of mine, Dr. Joe Natowitz, who many of you may know, to look for that in some data that they had taken to see if there were these enhancements in the production of the breakup of excited nuclear matter at these excitation energies that were predicted by Wang. Okay, so once you have an excited toroid, then how might it break up is the question. And so one certainly could have a rotating fluid, and this is a fluid dynamics. This is not actually a nuclear example, but so you could rotate your drop of liquid, and you could form your toroid, and if you keep rotating it, it may break up. Okay, and here's a little demonstration of what might happen there as these instabilities set in, and this toroid of fluid breaks into many pieces that, as you can see, are approximately the same shape, right? And so this was actually looked at by many people, and I actually went through and have a whole nother set of the numerous theoretical and experimental searches for toroids that really was prompted by Wang's initial investigations. And then Luciano Moretto was involved in many of this, and really many of the nuclear groups throughout the world went after looking for toroids. One experimental example is that from Michigan State in the 4-pi group, where they were actually in krypton plus niobium, they were able to see that as you ramped up the beam energy, you went from something where you had a low multiplicity and high charge asymmetry to getting something where your charge similarity was quite high and your multiplicity was high too, and said this was evidence for this toroidal breakup. As I said, this whole idea really came then to Texas A&M in terms of looking for this preferred exit channel in silicon-28. Okay, so the other thing to make sure we're aware of, silicon-28 is an alpha cluster nucleus, okay? So the idea that you would break up into many fragments of similar size, and if those little fragments were alpha particles, that could be a nice signature for this toroidal shape breaking up. Okay, so what they did was to use Nimrod to measure this reaction. So if you put a carbon target in Nimrod, so the idea was to take a silicon-28 beam from the cyclotron, react it on a carbon-12 target, the silicon-28 would get excited and break up into 7 alpha particles, which would then go into Nimrod and be detected by Nimrod. This is obviously a picture of Nimrod and a single module where you could see what we have is silicon-silicon cesium iodide. So the identification is by delta EE. It's very clean for things as light as alpha particles. I will say that this experiment was not done to look for toroids. It was an experiment that was done to look for other things, and as many of you know, we write event data to disk, and we used to write it to tape. We still call them physics tapes. And then you can often mine that data again and again for other signatures. And so at one point, they went back and looked at this data to see if there were signatures of this 7 alpha breakup that would in any way indicate it had come from a toroidal nucleus. Okay, and when they reconstructed the excitation energy of that 7 alpha breakup channel, you could see they have some what look like potentially enhancements in the production at energies that were predicted by Wang to have stable toroids, okay? Again, like I said, this was not intended to measure this, so you can't blame them for the statistics. They had this indication. They went through and tried very carefully to do a mixed event analysis using AMD and Gemini, normalizing in the gray area there where you were not expecting any resonances, subtracting it out, and getting this spectrum where it looks like there may be some enhancement, fitting that spectrum, and then coming up with this prediction that there were, in fact, toroids that showed up in these 3 excitation energies with this full width at half max and a predicted cross-section based upon calculations and that data. But very notably in that paper, they did say clearly this should be followed up with another experiment that's actually intended to make this measurement. And so if you fast forward then a few years, a very bright student, Andy Henneman, joined my group, and we were talking and said, okay, we should go look for these. We had a detector called, well, we have a detector, we still have it, called FAUST, which is a forward array using silicon technology, which had recently been upgraded to replace the silicons. It was originally built with the silicons as single pad silicons with a DATL, which is a dual axis, dual lateral position sensitive detector. And what this allows us to do is get much, much, much better position information on the alpha particles, which lets us get much better resolution in terms of the excitation energy because we know the angles much better. FAUST is actually ideally suited for this because it is a forward angle detector, and you can see this is the coverage which goes from one degree out to 36 degrees on the sides with some additional on the corners out to 45 degrees. So the efficiency of Faust for detecting these things is quite high, and the position resolution and the energy resolution are excellent. So Andy went after trying to get these 7 alpha states and to see with much better statistics and much better excitation energy resolution, would we see the resonances that there were indications of in Nimrod. And actually his prediction of this is it would stick out like a picket fence if they were there at the cross sections and full width to half max that was predicted. Where am I going? Okay, so here's a depiction of the silicon detector that's used in Faust, and this is key because it gives us the resolution. And so if you have a particle that comes in, the charge splits across it, holes on one side, electrons on the other side, you pick up the 4 signals, and then by adding together the signals, you get the full energy either from the front or the back, so you have 2 measures of the energy to make sure that you're getting the same thing, and you get the position by the relative splitting. So you get the position both in X and in Y, and you get the full energy. What that looks like is this. This is a position spectrum taken with a thorium source just in front of, this is a tantalum mask that actually had to be very carefully done because each of those slits is at a very particular angle that will actually illuminate the ring of Faust that it's going through. This was actually quite a feat to even just get made. But you can see then across the 68 detectors of Faust, the really nice energy resolution and the really nice position resolution that we can get with this detector. This will then let us get those particle angles much better to get the excitation energy much more precise. Okay, so then of course we did an experiment and we collected a lot of data. So we ran for 6 days on the target, which was the silicon 28. We ran a number of other different systems. So we ran on aluminum 27. So we were doing some reactions off of something that was not an alpha target, an alpha cluster nucleus. We ran inverse things. We ran silicon on silicon. We ran the carbon on silicon, just so we could see if there was any systematic issues that we wanted to make sure we could account for. What I'm going to show you here is really just the silicon 28 on carbon data, but I can tell you in analyzing all the rest of it, there are no gremlins in there, okay? And I'm happy to talk to anybody about any of the rest of the measurements, but we'll just look at the silicon 28. Okay, so this is what the delta EE spectrum looks like for the silicon versus the cesium iodide that sits behind it. So you get really nice resolution all the way, let's see, you can see the bands all the way up through the silicon, and you can see there's really isotopic resolution all the way up as well for all 5 rings. One obviously does a linearization through some point picking of this so that you can actually do the individual identification of the isotopes, and then you can see how clean the alpha particles are, and there really is only a few percent, 1.5% contamination in the helium-4 gate. So when we see these 7 alpha exit channels, we really have a 7 alpha exit channel. Okay, so one thing that we really wanted to look at, and I've been harping about the position resolution of Faust, and what you can see here is what happens if you actually reconstruct the alpha decaying excited states of various nuclei, okay? So in this case, this is a lithium-6 breaking up into a deuteron and an alpha particle. And what you see is when we use the actual position resolution of Faust, you get the peak by the black line, okay? If we did not have the position resolution because of the charge splitting, and we had the old silicon detectors, it just was a 2 centimeter by 2 centimeter detector, we would get the red line, okay? And that's the difference that that position resolution makes, okay? So you can see it across many different resonances that you really just can really, these resonances pop out when you have the position resolution that we do with Faust. And you can see that this was just a really nice example that Andy did looking at the 3 alpha states in a carbon-12 breakup, and then you do that and you can just fit it and everything lines up. And so that's all really nice. This actually was also used to be able to help identify particular detectors that might have been slightly out of alignment, or that we had to just make sure that their alignment was set. Using this resonance and sharpening up the resonance as one went through the calibrations was really quite a nice thing that Andy did, and allowed us then also to get a good estimate of what our uncertainties were, because we could understand it quite well. Okay, so now let's look at the excitation energy spectrum from that 7 alpha breakup. So this, just to bring us back, was what we were looking for, is peaks at these 3 energies. And what we saw was this. So what you see is essentially a very smooth distribution with no apparent peaks. When you do this fitting, and so we did the same mixed event fitting with the AMD and well, we did both mixed events, and then we did this also with AMD and Gemini. And what you see is you can get your mixed events to line up, and then you get this enhancement over here, and you can do your subtraction. The mixed events don't work exceedingly well when you're trying to reconstruct a whole system like this. Mixed events have been used, many of you know, for looking at particle-particle correlation. So if you have a large system and you're looking at 2 particles coming out, you do your mixed events, and it's a great way to subtract out any random background. When the mixed events are done on essentially the whole system, it's more complicated, and we tried a lot of things in looking at different kinematic cuts to restrict the data, and there's just something about trying to do mixed events for whole systems like this. But you see essentially the same overall behavior as the old Nimrod, but you see really no peaks that stand out at the appropriate excitation energies. Okay, so just talk a little bit more about the background. So, like I said, we did mixed events. We also then tried to use AMD plus Gemini, okay? And if you even just look at the AMD plus Gemini in terms of real events and mixed events, the mixed events don't come back and give you the appropriate background. And so that made us hesitate a little bit about relying on the mixed events or the AMD plus Gemini to give us our background. So what we wanted to do was to find another way to see, was there any idea that there were peaks above what could be described as a uniform background. So we went ahead and fit the background with a polynomial, and this was fit with actually many polynomials from about 2nd order to 12th order. The 9th order was the best. We wanted to make sure that it was in general fit the spectrum and had the least chi-squared fitting there. Once you've done some fitting of the background, you can get the yields of anything above the background, or above or below if there's any peaks. And then just because the error bars will matter depending upon what the number of counts are in there, we went to looking at a standard residual. And so here you can see this is where we would have essentially 1 sigma, and there's no real outliers that would tell us there is a peak at a particular excitation energy. So what we wanted to do was then say, okay, so we don't really see anything, but maybe if the peaks are really small, the cross-section is just much smaller or much wider. So we went through asking, well, what have we expected to see, and what can we say? And so we can look at what we expected, and if you look at the full width at half max that was measured in Nimrod, you have to take into account what is the resolution of the detector, and then what is the intrinsic resolution from the measured resolution, okay? And because we have a different device here, and our resolution for the full width and half max is much better with the Faust and the position resolution, we have to do this to get to the intrinsic resolution. And then in order to try to get an idea of what the cross-section might be, one did the same thing of relying on a model to predict what the frequency of seeing these excited states would be. So we went ahead then and said, okay, if there was an expectation based upon Nimrod, this is our data, and then what would it look like? And so we went through this modeling of using this kernel density estimation, which is a KDE, where we could essentially sample what is that distribution. So we define a distribution that looks like the background. We can sample it so we can then get an idea of what the statistical error is involved in all of this. And then you can embed in that, add on to your background a peak. So if we had expected a peak like this is what it would have looked like in our measured spectra, okay? And then the KDE can actually sample the distribution, which is the background plus the peak that you were expecting to see, okay? So if you go ahead and do that, and you say that the width of the peak is a half an MeV, then you would have gotten a distribution that showed these peaks, and when you subtracted it out, it would have stood out like that, okay? Clearly, we didn't see anything like that in our data. But, well, maybe the peaks are actually wider than that, and actually you just couldn't see it because the Nimrod had a wider ability to check the full width and half max. So you could go ahead and do this calculation where you say that the full width at half max is 4 MeV, and you would still see these enhancements and you would still see peaks. You can go as far as to say, okay, what if it was 9 MeV, if it was really wide? And then it gets a lot harder to say that whether there are peaks there or not. So we used this to be able to help us set some limits on what our data was consistent with. And so we did the statistical likelihood analysis. So the cross-section is corrected for the efficiency. The intrinsic width takes into account the resolution, and the background, we have to make sure that we're accounting for the background uncertainty. So let me explain what we're doing here. So the black data here is the KDE, okay? So that is the sampled background off of this distribution that fits the data. The blue is the peak that we would have seen. If there was a peak of this size, it would have shown up there. Now, if we go ahead and fit this, and we ask it, what is the standard residual off of a model that agrees, that includes just the background, okay? So if we're just looking for the background, and we did that, we would see this red peak in our standard residual. So at the excitation energy, we would see a significant enhancement. Then if we did the model where we added in the peak and we get the blue line, and then you ask for the standard residual, you don't get an enhancement, okay? And you see that in the inset here, where basically the cross-section of any enhancement, if you include the peak that the fit, including the peak that you're looking for, is really right around 0. If you don't include this peak in generating the data that you do the fit for, then you actually see these high cross-sections at particular excitation energies, and that would be the signature that you get a better fit when you include that, so you must include that, okay? This lets us then sample this at many different excitation energies and many different widths. Okay, so we can go ahead and go through that and do an iterative comparison of this model across changing the intrinsic cross-section for this 7-alpha breakup from a toroid and changing what is the frequency of the measurement, okay? And then we can go ahead and get what is effectively this data here. And let me kind of explain this data because it's a pretty picture, but it's a little bit to digest it first. So as I said, we went ahead and we were able to change what is the frequency in which you would see this breakup. So effectively, that is the cross-section of that exit channel as a function of the intrinsic width, okay? So what we're doing is searching the whole area of saying, if these resonances existed at a particular cross-section, at a particular intrinsic width, what is the probability that we would see them, okay, given everything we know about our experimental setup? And so then we have in the color coding, effectively, what is the probability of the peak model being more likely than the non-peak model, okay? So that's fitting it with a peak that represents that cross-section and that full width and half max versus fitting just a background, okay? So anytime we are up here in the red, it really means that the probability of that cross-section, of us missing that cross-section, if it were there, is like not there, okay? And what you see is that as you go down, and you can pick any intrinsic width you want. You could say, okay, so let's look at 1 MeV of intrinsic width. Once you get to a very low value, the probability that statistically we could say with certainty that it was not there, you can't say below a certain cross-section, okay? And so then we set these 95% confidence limits, saying that anything above that with 95% confidence, we would be able to see it statistically. And then as you go below that, you would see that you lose your sensitivity at very high width and very low cross-section, right? That's just what you saw that intuitively a couple slides ago, but this then actually goes through and is in a very statistically rigorous fashion, lets us set this upper limit to the cross-section. And so here we have this upper limit to the cross-section, and you can see for the 3 states that we were aiming to measure and were predicted in the Nimrod data, that our upper limit to the cross-section is here in these solid lines with the arrows down, and then you can see that compared to the Nimrod cross-section. So my message is that in this particular data set, where we went after looking for a very particular signature, it wasn't there, and it wasn't there at a level where we can set the cross-section down to 20 microbarns. So if the cross-section for this resonance is below 20 microbarns, we would not have been sensitive to it. And and as you go to a larger width, that sensitivity goes to even higher cross-section. So I'm just going to go ahead and summarize because I know that I'm close, and George has been nice and given me 5 minutes, even though I'm just taking advantage of that extra time that was given to me by the introduction here. That we went ahead and we studied the 7-alpha breakup using Faust, this forward array using silicon technology that has these position-sensitive silicons on the front of it. And this excellent angular resolution and energy resolution is key to this measurement being as statistically precise as it is. There was no strong evidence of resonances, and you can see again just how a nice uniform background fits that pretty well. And one thing I didn't talk about, because I didn't realize you guys were going to give me an extra 10 minutes, otherwise I would have put it in, was all the work that we did studying momentum shape observables. So looking at sphericity, coplanarity, and all of these other things, because certainly if you go back through the many searches for toroids, people will say, well, you'll see an enhanced coplanarity you know, as opposed to sphericity, it'll look like a disk and stuff like that. Lots of data and investigations along those routes that I left out because of time. But we did perform this statistical likelihood analysis to establish the upper limit. And just to point out again that if there had been a peak like this, we'd see it in the standard deviation. And from that, we're able to set this upper limit for the cross sections. And so, I'm sorry to say, we did not see any toroids, but Andy made a fabulous measurement, and we've got gobloads of data. So people that have interesting ideas of what we can do with this amazing data, I'd be happy to chat with you because we've got lots of good things. And anyway, always need to thank, once again, Andy was fabulous. And then a lot of work by Chris Hagel, Brian Harvey, who's a grad student who's really the mastermind of all the statistical analysis, Alan McIntosh, the rest of the SJY group. Again, the Cyclotron Institute in general, we've got a great facility. Again, if I'd known I had time, I'd walk you through the facility, and support by the Department of Energy and the Welch Foundation. And you for your attention. Thank you very much.
Thank you very much. So thank you very much for this motivating, exciting, and very educating talk. So the paper is open to questions. Yes.
So thank you very much for your nice job, because it's really rare to see such say detailed statistical analysis, typical nuclear data. But I have two questions. One is regarding this statistical analysis. You mentioned that your particle identification is very clean, but you mentioned that about 1.5% survive. I mean, it's helium-3. And you have to combine these for 7 alpha events. You get something like 10, 15% of data where you have at least 1 helium-3 if you make the OR of all of these. So at the very end, I mean, this very detailed analysis where you are looking for a teeny peak over a big background could be plugged by a much bigger background coming from particle identification, I mean, residual, let's say, no?
The uncertainty due to particle identification is built into the uncertainty that feeds the model. So everything that we could identify as an uncertainty, so the small amount of helium-3 contamination, there's a very small amount of uncertainty because we don't have exact position, we have pretty good position. All of that is built into the model in terms of being able, if you looked at the KDE, there's a band there that gives you the uncertainty of what is realistic in the cross-section. But it is true that a very small cross-section could still be hidden there, no doubt about that. But the limit really is at the smallest full width at half max, 20 microbarns, and certainly higher for higher full width at half max.
Another question regarding the physics. I remember a few years ago, Valentin Nesterienko was talking about toroids and other modes of excitation. But it was pointing is, let's say, optimal excitation energy at much lower, about 20, 30 MeV excitation energy, I remember, not 100 or something.
There are various different models that go after predicting this, and if Aldo Bonasera was here, but he's not, he would tell you the work he did with also predicted wider overlapping states at lower excitation energy. So it really depends upon which model you're looking at would predict different things. And so we certainly, our data cannot rule out things at lower excitation energies. We very much went after trying to look at this one prediction and trying to measure that well, and I think we did that. Certainly doesn't say that toroids can't exist or don't exist. It's just this signature, if it's there, is very, very small.
Thank you very much. I have more technical question concerning the detectors, because I have to admit my ignorance is the first time that I heard about the types of detectors. Who is producing and commercializing them? Are they commercial?
Yeah, we developed them in conjunction with Micron, and so you can probably just buy them from them right now. Yeah.
Yes. My question is about the lifetime of these shapes from a theoretical point of view. Do you have any opinion about this? The theoretical prediction, what they have lifetime of these shapes?
If the lifetimes are very short, they will be very hard to see, right? I mean, this is all tied in with what you would have, what you would say the cross section is, and it's related to the lifetime, right? So. Yes. Okay, so here's a few of the different things that we did, but we've looked at many of the different exit channels and actually tried to look through a 7-alpha event that contains a beryllium-8 in it, or a 7-alpha that contains an excited carbon-12 in it. Just probing in all these ways, is there any way that there's a subset that is more likely to either have or not have the toroidal shape? And unfortunately, that, along with many of the sphericity coplanarity explorations and everything else, was not able to pull out anything that was a toroidal shape. But lots of beautiful, because of the resolution, lots of beautiful data on other resonances, yeah.
I think I could take one more question. If there is no question, if there are comments or further questions, we can parallel group.
So the natural question, thank you. So the natural question arises, is it possible for these virtual electron-positron pairs to tunnel through the vacuum and become real particles detectable by instrumentation? The answer is yes, and was given by Julian Zwinger in the 50s with the so-called Zwinger mechanism, which we'll describe here. So this, the Zwinger effect is essentially the creation of electron-positron pairs out of the so-called nothing state, the vacuum, which of course is far from empty, but contains a lot of particles and antiparticles popping in and out of existence. And in the case that these particles are spin-half particles, they follow the Dirac equation. Now, it is well known that the Dirac equation particles can actually satisfy approximately the Klein-Gordon equation for massless particles, with a minor spin-dependent term that we consider a higher order effect, so I will not take into account here. So for the Klein-Gordon equation, we have the three-dimensional momentum and the mass of the particles. And then we can mathematically manipulate this by breaking up the momentum into an axis x, which is the tunneling axis of the pair, and a transverse momentum, which is perpendicular to the previous one, yielding a Schrödinger-like equation with the transverse mass and an effective potential containing the actual potential of the particle and antiparticle, as well as the total energy. Of course, the right-hand side is 0, which meaning that the effective energy for this system is also 0. What we do in this project is that we study the tunneling of the antiparticle and particle pair through this effective potential. And to do that, we use the understanding of antimatter in terms of the Dirac sea theory. This is actually the most difficult slide for me to present. If this is understandable, the rest will follow suit. So let me try. The Dirac sea theory tells us the following, that the peculiarity of the Dirac-like coordinate equations that give particles with negative energies, and I'm talking about mass and kinetic part, can be understood in terms of a positive energy spectrum that starts with the minimum energy, which is only its mass, meaning that the particle does not move, and a fully filled negative energy spectrum, a sea of states, if you will, with a maximum given by minus the mass. Of course, when we add the potential, the situation is similar to the top panel here, where we have on the y-axis the potential plus the mass. This is the long dashed line is the upper limit. Of course, the x-axis is the dimension that we're discussing for the tunneling. The solid line gives the potential, and the short dashed line is the potential minus the mass, which is the maximum of the fully filled negative continuum. The Zwinger mechanism can then be understood as follows. Essentially, the particle is initially in this region here, in the negative energy continuum, as long as it is virtual. At some point, due to the presence of a strong field, it can tunnel through the potential all the way over here, above the long dashed line, into the positive energy continuum. This, of course, leaves us with a particle with real energy and a hole with the same mass and the opposite charge, which is, of course, the antiparticle. We can see the same picture here for the effective potential. The effective potential situation, we see here that the particle is initially trapped here in the negative energy region, tunnels through the effective potential, the vacuum, and then reaches the positive energy continuum. Let me stress something here. The energy that the potential of the particle right here has at infinity must be smaller than the energy that it has at x equals 0, when the proton and the electron, and the positron are on top of each other. Why is that? In order to be able to exit a tunnel. And how much smaller must be? At least the gap size, that is twice the mass of the particle. That means that when the particle exits the tunneling state, it should be repulsed by the potential. This is not a trivial fact, because it actually limits the cases that we can use this mechanism to understand the pair production. For example, Dr. Aldo Bonasera and now Dr. Thomas Settelmeyer have studied black hole radiation, the Hawking radiation, in this mechanism, and it cannot be explained by that, because gravity, as we all know, is an attractive force. So we need repulsive forces only. Our model is then based purely on this situation. We have two symmetric nuclei, and we assume that this is the z-axis, the axis of the collision, and then we have initially at an axis perpendicular, the x-axis, the electron-positron pairs. Initially, the positron is on top of the electron, start at x equals 0, tunnels through the potential in this direction, and then exits and is repulsed by the potential. Now, this is an interesting perspective, because it may allow an enhanced fusion cross-section and perhaps even completely change the dynamics of the system. So this is the motivation of our study. It is apparent quite easily that the model, as it was in the previous slide, has a problem. When the electron and the positron are on top of each other, the 1/r Coulomb potentials tends to minus infinity. We can get arbitrary negative energies. So we need a cutoff, a screening, which is given by this exponential factor over here, with xs being the screening length. This screening length is a property of the vacuum and actually can be fitted from experimental data, but for the moment we are using its classical value that when x tends to 0, we get twice the mass of the particle. That is the minimum the minimum energy that the field must possess in order to create this from virtual pairs to become real. So here we see, for example, here without the screening, the potential that is given in the y-axis tends to infinity, while this tends to little more than 1 MeV. Taking all of these components into account, we can construct the model with the potential for the positron, which is given by a term with the interaction of the ions, and the screened Coulomb with the interaction of the electron, and then plug it into the formula for the effective potential and the transverse mass. This panel is similar to the previous one I showed, so we have here short dash line for the maximum of the negative energy states, long dash line for the minimum of the positive energy continuum, the solid line for the potential, and actually we see the two cases that are limiting for the effective potential. So if we set the effective potential to be 0 at x equals 0, we get these two solutions. Now, we can see that the green solution is not acceptable. Now, why is that? Because it's already real. It's already above the positive energy continuum at x equals 0. So that means that the effective potential is constrained to at most be 0 at x equals 0. So this puts another constraint to our model. We have also taken into account the energy conservation. The energy of the ions, the kinetic energy of the ions before and after the pair production must change by this amount here. And we also require that the energy of the positron is initially at the negative energy continuum, so it's below the potential minus the mass, which in total implies that the ions must gain at least twice the mass of the particle. And that is very important because, for example, for an electron, this is almost equal to 1 MeV. So we have a fusion in stellar conditions, for example, that where the gamma of energy is very small. This can completely change the situation. Now we'll discuss how the tunneling is done. Actually, I will discuss this also in the afternoon in the astrophysical talk. The tunneling is performed via the so-called imaginary time method. So the basic characteristics of the method, although we'll explain later, they're assumed that the tunneling is performed through an expression with the classical action A below the Coulomb barrier. So from the two turning points, we integrate it, we take the action, and we see that the tunneling probability PT is inversely dependent on the action. Higher action, smaller probability. Very interestingly, we see in this plot here of the tunneling probability as a function of the distance of the ions, that the probability is essentially constant up to a critical value for the distance of the ions. And actually we see that this critical distance increases as the kinetic energy of the ions, the extra kinetic energy, decreases. So if they gain 2 times the mass of the electron, the critical distance is overweight to 17 Fermi, while if they gain 6 times the mass of the electron, the critical distance is overweight to 9 Fermi. This is understandable because the moment we create one pair, then they move much faster, so the tunneling probability will decrease. We, of course, would like to know the cross-section, which is for the pair production, which is given by this formula, which is reminiscent of the usual partial wave expression, with a minor tweak here, which takes into account the characteristic time. So we have delta tau. Delta tau is the characteristic time of the pair production from the Heisenberg principle, and tau, which is the time that the ions are able to produce a pair. So the time from the classical turning point, the Q value is equal to the Coulomb, all the way over here that the ions have the critical value where and the pair can actually be produced. Now, due to the mathematical structure for the tau, we can see from this plot of the cross-section as a function of the center of mass energy for the pair to be produced, that there is a minimum center of mass energy needed for the pair to be produced in a nuclear reaction or a nuclear disintegration. But, of course, this is a model dependent. The next thing we would like to see in a possible experiment or a possible theoretical work is a spectrum. The number of positrons as a function of energy over a certain energy d. Elementary, this probability is given by a simple proportionality, so the number of the positrons is equal to the probability, the fundamental probability of tunneling, times the time step dt over the characteristic time delta tau for a pair to be created. And using now the energy conservation, we can change variables and construct this simple formula. This is inversely proportional to the charge of the ions, the velocity of the ions, the tunneling is in proportional to the tunneling probability, and as well as the distance of the two ions. Now, of course, the question about the velocity is which velocity are we using? As I said, after the pair production, the ions gain kinetic energy. So should we use the velocity after? Should we use the velocity before? Or something between the two? We leave this as a free parameter. We include this parameter vita here, and we give it all values from 0 to 1. When vita equals 0, we assume the velocity before the pair production. When we give vita equal 1, we take as the velocity after the pair production, and n in between is a linear combination of the two situations. So let's see some results. Here we have the californium-52, which is a nucleus that fissions with 3% and that the alpha decays with 97%. These plots here are actually the spectrum of the positron. The y-axis has dN, dE, and the x-axis has the energy of the positron. The only difference is that in the top we use vita equals 0, meaning that we take the velocity before the pair production, and the bottom panel shows the velocity after the pair production with vita equal 1. The blue line here corresponds to the fission part with using only Coulomb trajectories. So we start the calculation at distances far enough, so the nuclear part is not important. Now here we see that the gray part has only also Coulomb trajectories, but describes the alpha decay. And this is almost equal to the total, which is given, if it is possible to see here, is not a very big picture, by this dashed line. The red part is actually one of the most interesting cases, because it also shows a fission dynamics, but taking the results from the NEC model, which I will explain next. This is a Vlasov type, a code that enables us to take into account the nuclear part of the reaction. Interestingly, we see that there is a small bump here, an enhanced probability for pair production, during the point that the two nuclei have formed a neck and they start to fission. So here we can create more pairs. And we also see that the divergence leaves this plot because when you take the velocity before the pair production, initially the nuclei are at rest, so this gives us a divergence at high energies. This is the NEC model. So I will discuss it briefly. The NEC model is actually a Wigner transformation of the time-dependent Hartree-Fock, where it assumes that during the fission or fusion, the nuclear volume is conserved, so this creates a neck for the two nuclei, given by this shape here. So essentially, we break down the problem into two fundamental degrees of freedom that are evolving, the neck radius Rn and the distance. And this model has actually been used by Dr. Aldo Bonasera to describe very well the fission dynamics. This is for californium-52, the total kinetic energy, as a function of the mass. These plots are the same as before, but for alpha decay here and here for symmetric fission of nuclei using only Coulomb trajectories for several heavy ion systems. I will not spend much time here because of time constraints. And now we'll briefly discuss the limit of no screening. So in the case that the screening is taken into B0, so we have no screening in between the positron and the electron, we get a situation where we have two double humps in the effective potential. That means that the positron must tunnel through both of them and also be in phase in order to have the tunneling situation and become a real particle. This is quite interesting because it can actually create resonances. For carbon here, the top refers to the probability of tunneling for carbon as a function of energy, and is the phase as a function of energy. We see that there is a smooth increase without any resonances. Below have uranium on uranium, which we see a resonant increase, and this can be explained by the values of the phase. And this is actually very interesting because in this limit of the model, some more or less controversial data from GSI from the 80s that showed uranium on uranium collision can have the same behavior. Concurrently, we are working also an experimental pathway for this process. So we have a spectrometer called G-Spec here, which has two imaging plates on the sides and one on the back, which can collect the particles that come from this small hole here, and then can be scanned with a laser to give us the data. We have a magnetic field perpendicular, so they are curved. And I'm seeing that already standing up, so I will almost conclude after I discuss our preliminary data for the spectrum here. So we have a spectrum of a mixed source that contains heavy nuclei, and then for the californium-252. And interestingly, we see that the bump from the scission is also presenting in our experimental data, and the trend, the increasing trend that we see in the alpha decay, which is mostly the low energy part, can also be seen. I would like to conclude now the talk. We see, both experimentally and theoretically, that strong electric fields by heavy ions are more than enough to create real electron-positron pairs, and this can have actually important implications for the dynamics of both reactions and disintegrations. While from this situation, we also learn the properties of the vacuum, as well as the several dynamics below the Coulomb barrier. At this point, I would like to convey the thanks of my advisor, Dr. Aldo Bonasera, to the committee for the invitation, and all of you for your attention.
Yes, one or two questions.
As you know, researchers since long ago study binary bound system of electron-positron pair called positronium. This is a purely leptonic atom, and it has bound states as the hydrogen.
Mm-hmm.
Does it include it in your model as a separate channel?
No.
Because it is produced from electron-positron.
Yes, so it's not included in our model because usually when the positron exits, it is immediately strongly repulsed, and also usually it exits at some hundreds of Fermi. So with this low energy regime, we do not take this into account. Perhaps the energy is higher in the situation of the production.
The energy, of course, the bound atomic energy is of the order of 30 kV like.
I mean, the center of mass energy of the ions is higher in the situation where the positronium is produced, or?
The total energy, of course, is of the order of the two mass.
I see. Yeah, no, we're not, yeah. MV. Okay, so yeah, we do not take this into account. Perhaps it would be useful to think about in the future. This is an ongoing project, of course. So yeah, we assume that the positron is ejected almost immediately. So this is actually a very good question, because I can stress that this is, for the moment, a perturbative calculation. So I assume that the mean dynamics remain more or less the same apart from the production of the pair. If that would be the case, perhaps we should do a non-perturbatively approach.
One more question. Yes.
Just for information, you suffer some extra, when you produce this pair, you suffer some extra colorings or some kind of recombination here? Particles, ejected electrons, positons.
Yes, so they are collected with normal mechanisms upon the imaging plate. So the pair production on the imaging plates or the change of the voltage, and then we scan them after some time with a laser. I actually, excuse me now you to remind me, I forgot most importantly to say that this experiment is in collaboration with the University of Texas at Austin and some on their laser facility. So yeah, this group does the experiment with the scanning part of the experiment after some time.
Because we have a discussion with Aldo about this background produced of this example of the photographic plate that you have.
Yes, so for the moment we're currently in the analysis of the data, so there might be some contamination from that. Yeah, these are preliminary results unsubtracted for the moment.
Okay, so let's thank Theo. The next talk by Professor Vardaci.
I could kindly ask all the speakers, if possible, to stay in the podium, because we try to record this workshop, if possible, and use the light pen of the computer.
To use the?
If it is possible, to stay there
Ah, okay.
and not to go up and down.
Okay, I'll try. Okay. Okay, hello, everyone, good morning. Let me start by thanking Athena and the organizer for this invitation. It's my very first time in Greece, the land of some of my relatives, and I'm very, very, very happy to be here. It was very emotional for me to be here and to travel along this country from Athens to Ioannina on the bus. It was really an amazing trip. So thank you again for all the emotions that I'm receiving here. Okay, so I will switch gear a little bit because now we go in another area of the Segre chart, but much lower energy. And I show you this very nice figure of a photo concerning Naples. You know, Naples was founded by Greek in the 18th century before Christ. So it's it has a very strong trademark from Greece. So let me see how to change here okay, so I have to change only here, right? So, okay, so we are talking about the search of elements, new element in the superheavy island, and how fission is important for such kind of study. So obviously this study is in collaboration with many people, some from Dubna, some from Romania, and obviously from Naples. See, this is the famous Segre chart, and just to give you an idea, we are going to concentrate on this area, which is mostly unknown area, which has atomic number between 114 and 126. This area was predicted to be populated by very stable nuclei. It's so much stable that this is called the new island of stability. And the stability of this, let me see if I can go through easily, okay. The stability of this element was predicted in 1966 by a group of 3 people, Sobichensky, Kalinin, and Garev, who tried to say, okay, let's increase the number of protons and neutrons in the shell model. Let's see what happens. So indeed, they found out there was another set of magic nuclei at around 114 and 184 neutrons. This area, you can see, is very much separated by the known land, this is the area of the actinides and uranium and so on. And obviously, all of these predictions started a new era in which everyone tried to see if it was possible to produce such nuclei. So this pink squares here show what is the situation now. By using fusion reactions, it has been possible to produce many nuclei in this area. And you know, the heaviest one is oganesson with the Z equal 118. This is the heaviest nucleus known so far. And you know, this nucleus closes the 7th period of the periodic table. And one of the prediction on the chemistry of this element tells us that this guy is not a noble gas. It's going to be probably solid. And so this means the end of periodicity in the Mendeleev table. So there is a lot of new physics that will come also from the chemistry of these elements. Now, the point is, what is important, how fission is important to produce nuclei in this area. Why, first of all, these nuclei are stable. These are stable only because of shell effect. If you consider a liquid drop, this is a typical potential of liquid drop. You see there is a barrier. Okay, but for super heavy nuclei above 103, there is no such a barrier. The effect of shells is to drop the ground state so that a fission barrier appears. So the stability of this nuclei is only due to shell effect. Shell effect produces a barrier, fission barrier, and obviously the stability is connected to the depth of this, so let's say the height of this barrier, and also on the thickness of this barrier. So first of all, it's clear that only this nuclei with Z bigger than 103 can exist only because of this effect. This effect can be calculated, with the method called Strutinsky method. This was invented also in the 60s. Let's say now how we can test this possibility to create super heavy element and why fission is so important for this nuclei. So you know that in order to produce super heavy elements, there are only so far there's only one mechanism, which is called fusion of this nuclei. So after capture, what it can happen that the system can in principle decay immediately into fragment. This is called quasi-fission because the charge involved here is so high. We're talking about the two guys with a lot of protons. So it's very difficult to create a compound system. So usually in test book, we know that if we pass the fusion barrier, indeed these two nuclei should fuse. This is not true when you increase dramatically the proton number. And so what happens is that the system does not stay together a long time and will decay again into body. Eventually, some of this path will go in complete fusion. And once again, what it can happen, this guy is too heavy, too much excited, it will go into fission, or eventually only a tiny part will go into evaporation residues. See, this is 1 over 1 million fusions indeed can produce a super heavy element. This is why this cross-section are the order of picobar or femtobars. So clearly, in order to arrive to this point, we need to cross these two places, these two parts. This bifurcation here, this other bifurcation here. So fission tells us about the survival probability of a super heavy element. So now you know that, how do we know that fission is important? Fission is important because it tells us about shell effect. If we use a usual liquid drop model, we know that practically the mass distribution should be symmetric. But we know from measurement the mass distribution is mostly asymmetric, especially for actinides. And this is due to the fact that there are shell corrections, shell effect to be taken in consideration. Because this, in the potential, shell effect create valleys and depth, okay? It's clear that the only possibility to have fission is to go through this trajectory, and this trajectory end up into asymmetric mass distribution. So this plot tells us that mass of the fission fragment is very sensitive to the potential energy of the composite system. So we know that indeed the nuclei, because of shell effect, can fission in many different ways. And one very famous way is sorry, I cannot look both the screen and the computer. This is an example, the spontaneous fission of some nuclei around charge around 100. And what is interesting here is that you can see there are differences that are very important. Mass distribution is mostly symmetric, but the total kinetic energy has two bumps, is asymmetric. This tells us that there are in principle two possibilities for this nuclei to, oh, this is not working anymore. No, sorry. Okay. There are two possibilities for this system to fission. So in this case, for instance, this is the fermium. So the mass distribution you can see is mostly symmetric. However, the total kinetic energy is asymmetric. It means that we need to develop a potential energy surface that takes into account more degrees of freedom, especially in the shapes. And so this tells us that if we do this, we develop the fission decay as a multi-dimensional mechanism. You can see there are different trajectories, and this trajectory can lead us into different conditions. One in which the two nuclei are strongly deformed, and the other one which they are practically symmetrical. This gives us two different paths, which mean two different total kinetic energies. So there are many different ways in which nuclei can fission. We have also the opposite situation, which we have an asymmetric mass distribution, but symmetric total kinetic energy distribution. And we recently attempted also to describe how this total kinetic energy can be well correlated to the shapes. This is, I'll do this very quickly. These lines here show possibility to have some shapes for this kind. See, this is the mass of one of the fragment, and this is the total kinetic energy. Okay, these three models correspond to three different configurations. We start from very stretched, super long configuration, more compact and more compact configuration at the fission point. And you can see these are the data. Okay, the data tell us that if you want to fission symmetrically, the only possibility for the system to fission symmetrically is that we need to have a much stretched configuration and fission point. If we want to have more asymmetric mass distribution, then the configuration must be more compact. So the mass distribution is a very strong, and the TKE coupled with TKE is a very strong probe of the shape of the nuclei at the fission point. Now, so what is important for us is that now, if we consider all these values, clearly the dynamic, the trajectories can go in many directions, but in several directions there can be many barriers. So even the mass distribution, the symmetry of the mass distribution can tell us where these barriers are. So it's not only one single barrier, as we usually see in textbook, but there are many barriers. These are called also conditional barriers. So what happens when we go into the super heavy now? When we go in the super heavy area, we can see this is the super heavy area where mostly the mass distribution are expected to be asymmetric. Here in this area, this is mostly the area before the super heavy island. And here also the mass distribution is asymmetric, but there is a transition. This transition tells us that we go from asymmetric to symmetric and then to asymmetric again. So to study this transition becomes very important to extend the model. We usually let's say, fit on this region, lighter region, and then we try to extrapolate this model into this mass region. So in order to do this, obviously, we need to see other things which are very important connected to the fission. Say, this is the lighter part, and this is the super heavy part. Okay, we can see this is the mass of the composite system. Okay, these two guys represent here the mass of the heavier fragment and the mass of the light fragment, because mass distribution are asymmetric. We can see when we increase the mass mass distribution tends to be symmetric, and this is the case of fermium. Okay, the mass tends to be symmetric. Then when we cross this point, so we increase the mass distribution tends to be asymmetric. What is important here? The fatal shell, T132, is the strong core that drives the whole transition. Now, this point is not important only for studying how to reach the super heavy island, but it's important also for astrophysical problem. You know, in the art process, fission recycling is very important. And we know that the actual model predicts that in case of very heavy nuclei, mass distribution can be not only symmetric with two bumps, but can be have also four bumps. Can be multiple. There can be multiple peaks in this mass distribution, and this, in principle, is very important when we go into the fission recycling. So to study fission modes is very important also for this reason. But as I showed at the beginning, when we have two bodies, not necessarily means we only have fission. Because, as I said, because of the strong Coulomb field, in principle, the composite system cannot be created, even though we pass the fusion barrier. What happened here is that if we look now at the potential energy surface, we can see there are all of these trajectory, all of these wells that can be filled once we enter the potential during the entrance channel. So the system enters here and can come out in many of these valleys. It can come out in this direction, then we can have quasi-fission it can come out in this direction. We have quasi-fission without creating a composite system. If for any means, by any means, the system is able to reach this area, it may decay again by following this path. It means this part, quasi-fission 2, it can be populated both from fusion fission and from quasi-fission. So whatever we observe in this mass total kinetic energy distribution in this middle part does not mean that comes directly from fusion fission. It may come also from quasi-fission. So this area of the mass distribution is an overlap. So to have an estimate of the fission cross-section becomes a problem when we increase the mass, because these two processes live together. This is an example of how this happens for the case for helium. If we change the entrance channel, we obtain a mass distribution that looks like mass distribution for a liquid drop. When we change the asymmetry of the entrance channel, we can see that this figure disappears. We have these two wings, means that there is another possibility to create two bodies, and this is the case of quasi-fission. Clearly, this quasi-fission increases when we increase the charge of the projectile of the target. I'll leave this here just in case we can have a discussion later on. Now, what is the main problem that I would like to bring to your attention? What if we use our known model on fission barrier and extend this model into the region of the superheavy island? So we would expect, this is the magic number predicted by Sobichensky. Okay, this is indeed the region of the where we expect, according to the current fission model, where we accept the highest fission barrier. These two regions do not overlap. Why is this the case? Clearly, this is a big problem because the two models, the model predict the highest high probability survivance to the fission is dislocated with respect to what we have in the case of a shell model. How can we investigate? This is not only the Moller model. We have other models that predicted exactly the same situation. So this is the place where we expect the highest shell stability, and in that the fission is dislocated. But if we extend other model, see the fission barrier really can range many MeV. So this area is substantially obtained by extrapolating models known, an example for actinoids. And when we do this, clearly this model go in any direction. So it means we need to do something to understand better fission superheavy element. Now, how can we test this model? Clearly, what we can do, we can test this model on heaviest nuclei, but also on lighter nuclei. Why is this? Because they are more easily accessible. It's very difficult to produce heavy nuclei, super heavy nuclei, because of many limitations to the target, for instance. So the idea is to try to use lighter nuclei. And see, the same model that I showed before concerning the barrier, the super heavy element, it indeed predicts another area which was unknown, which is this red area here, which is an area of asymmetric mass fission that was not predicted before and is let's say, separated from the region of the actinides by a region of symmetric mass distribution. So the idea is that, well, before we test the model in the very far area of the super element, let's try to see how the model works in an area which is more easily accessible. Indeed, this area is area where recently there was found that an example for the mercury. We know that the mass distribution of mercury 180 was found asymmetric after beta decay, while it was expected to be completely symmetric. So an example of how difficult it is for this model to work is the following. When we look at this thorium isotope, you can see this is a mass distribution at different excitation energy. We can see here the fission modes. You can see these peaks here correspond to the asymmetric, and clearly we also have, in overlap with the asymmetric, also the symmetric component. But when we look at the model, this Moller model, the same model I showed before, you can see the mass distribution, for instance, for thorium-224, it looks practically the same. Okay, practically the same to what was measured experimental. But the problem is that these peaks are not in the same place. Here, these are around 90. Sorry, 90, this is around 80. So even though sometimes the mass distribution is more or less same shapes, the position of these wells are not in the same place. Clearly, this problem that is known in this mass distribution, when extended to heavier mass, clearly produce unknown result, like the one I showed before. Now, how can we test even more this model? And I finish with this experiment. This is a case which is very interesting, is in Mercury 174, 176. What is funny here is that this is the mass distribution symmetric at low excitation energy. We know from textbook that when you increase the excitation energy, shell effect wash out. And so the mass distribution tend to be symmetric because mass distribution trajectory are not sensitive anymore to valleys. Okay, so, but in this case, we see that the mass distribution at low excitation energy is symmetrical, but when increase the excitation energy, it tend to be asymmetric. So the behavior of this nucleo is exactly at variance with what we expect normally when we increase excitation energy. So if this is a good result, if it's good expectation from this model, let's see if this can be found experimentally. Now, to find, this is also the case for 178, 76. We can see more or less the same situation. Higher excitation energy is more symmetric. So lower excitation energy is more symmetric than higher excitation energy. So the same effect is not that strong, but it's also possible for 176. Why I show also this? Because we tried this one, but then for running this this experiment, we needed an isotope of ruthenium, and we couldn't find this isotope because it was bought all by one facility, so we couldn't find this ruthenium-76 on the market. So we switched to this other nucleus. And so what we did, we studied 176, 180. See, we have two different ends on the channel. Clearly, we have a problem connected to quasi-fission here, but I will not go into detail. We use the time-of-flight method to measure this mass distribution. With time-of-flight method, we can measure mass 1 to the primary masses before any kind of evaporation. So in order to this is a typical mass distribution we measure for this nucleus. And this is the mass, this is the quasi-elastic component, and this is the total kinetic energy distribution. We can distinguish here quasi-elastic and more dissipative phenomena. This is part connected to the mass distribution, mainly to this event which are down here, which are coming from mostly from fusion fission. Now, what we can do, we can take, this is the mass distribution expected from calculation, and we can solve, see, we can split this mass distribution in different fission modes. And this is what we obtained experimentally, mass distribution at 3 different kinetic energy. Remember, we wanted to see how excitation energy changes the mass distribution and how the component of quasi-fission changes with the excitation energy. And indeed, we found this effect. We found that a lower excitation energy, this is the component due to symmetric fission. When we increase the excitation energy again, we increase the part connected to the symmetric fission, which is the typical trend we expect. But when we increase even more, we see a drop in this mass, in the symmetrical part of the mass distribution. So for this kind of system, we observe this reversed effect for which we don't have an explanation yet. Clearly, the mass distribution is a very important problem. This is the case, for instance, and I finish. This is the case, for instance, of a heavier nucleus, where we can see 2 different models, try to predict the mass distribution of this nucleus, which is Fermi 256. We can see here the red curve is the molar model, and you can see it can reproduce this very well, the asymmetric part, but has a big problem in the symmetric part. But if we take a Karjan model, we can see just the opposite. We can reproduce very well the symmetric mode, but we not reproduce the asymmetric mode. This tells us that models needs to be much more worked out, and so most of the problem in this case is how many modes, how many parameters in the shape are included. But clearly, we need to work out this problem both experimentally and theoretically. And for this, I thank you for your attention.
Thank you very much for your very clean explanation of the field. You mentioned that, of course, there are very strong shell effects which require the fact that liquid drop should be, let's say, complemented with something like shell model calculations. However, in these heavy systems, it's very hard to make shell model calculations. No? So how the field take care of this fact?
Well, this is obviously a critical problem, and there are different approaches. There are not only the typical approach used by Sobuchensky. There are, let's say, more recent approach used time-dependent artifact calculations. And in fact, the diversity of the approaches means also the diversity into the prediction of what is the next closed shell. An example, Sobuchensky produced 114. Indeed, there are these two other models, which is it's a kind of stochastic mean field and time-dependent artifact. They predict two different shells. So 184 for neutrons is the same. This is funny. But what is different is for the atomic number closed shell, which is 120, 126. So it's clearly not known what is the best, obviously the best prediction. But one method, which was developed by Strutinski, also used by Sobuchensky, is to use the known masses. And when the masses are not known, so what we do, we build the potential for the liquid drop, and then we add the correction that come from the masses. So where the masses are very low, with respect, because you're reaching close to the shell effect, this produces a valley into the potential. The challenge is to predict the masses for the super heavy elements. And this is a mix of situation. Usually the different liquid drop models are used to predict the masses, very, very heavy elements. But what is one of the, let's say, the connection with this mass is the Q value of alpha decay. Sometimes to reproduce the probability for alpha decay is more easy, and then you take the masses from the Q value of alpha decay. So there are many strategies.
Differences in the result are only due to the different methods, or also to the potential that you start with?
Yeah, both.
Another point, you use only mean field calculation.
Yes.
So you don't have effects like pairing or...
Yes, usually pairing is included. Pairing is included. And this is done usually with an alternative method, which is energy density functional. In fact, pairing is very, very important, because whenever, let's say this, well, I don't know if I have a few more minutes, but to explain at least the spirit behind it. The spirit is that when you must include pairing, because if you don't include pairing, you cannot explain correctly the fission probability, because when you have a strong pairing, you have larger probability for fission. If you have a smaller pairing, you have sorry, the opposite. When you have a strong pairing, then, weak pairing, the idea is that you eliminate excitation energy by breaking the pair. But when the pair is strong, then you have much more fission. So the balance between pairing and the barrier and the shell effect is very, very important for the super heavy element.
What about the different potential?
Different potential is very important, but when you build the potential, what is important is how many degrees of freedom you use in the description of the shapes. Most of the time you need to reach at least the octopole deformation. If you don't reach the octopole deformation, you don't find the valley, and then you don't find the correct fission modes. There are other approaches which are completely, let's say, completely theoretical, in which the mass is obtained by solving the Schrödinger equation with some perturbation and take the mass from the ground state. So there are many. That's what we do with Karjan.
Maybe one more question and we go for the topic. Yes.
Yes, thank you very much for the nice presentation. I would like to ask, you mentioned the competition between quasi-fission and fusion-fission. But when you succeed to construct the compound nucleus, it might evaporate with neutron protons and leave the heavy residue at the end. Does this leave a kind of background to the data?
This
The compound nucleus may evaporate with
right,
particles.
right.
It leaves a heavy residue behind. This leaves a sort of background in the measurement, the data?
No, this is a very complex problem. You can have neutron evaporation along the way. Now, what is the problem? The problem is that neutrons can indeed be evaporated, can emitted into the whole time series, the whole process. Okay. Now, there are measurements made by this, but we need to be careful, because when we measure the fission fragment by using time-of-flight technique, we measure the primary mass distribution, the one that is obtained right after the scission. So if this fragment loses neutrons, okay, these are called secondary fragments. By technical time of flight, this secondary loss of neutrons indeed do not affect dramatically the mass, let's say the velocity and the position, because you only create a small cone, okay, small kick, no, by emitting a neutron. So by reconstructing the kinematic, you can have the primary masses. The only problem may come from neutrons that are emitted before, or before the system will split in two. Okay, but these neutrons are not to be very, very small, because the whole process is a very low excitation energy, very low, you're around the barrier most of the time. And so all measurements so far have practically disregarded any emission of neutron before the system will decay both in quasi-fission or into fission.
So we'd like to thank the speaker.
Thank you so much.